Hello, this is David Compertore at Lumetrics. I'm here in front of this apparatus to demonstrate the measurement of a wet cell and how it could be used to monitor the concentration of a salt added to a liquid. Right now, the cuvette is full of air. In fact, here we go. I'll throw the pointer inside and I'll block the beam, and that makes one of the peaks go away, the back peak. So that back peak is the back of the cavity in the wet cell, and the front peak is the front surface of the interior cavity of the wet cell. There we go. We'll block the full beam and show you that the peaks disappear. So if you watch the waveform below, the peak's gone and it comes back when I bring the pointer out of the way. Now if I'm in the back, I can still see the beam because the beam has already passed through. It doesn't affect either of the peaks. This is the probe. The beam comes out, the probe for the OptiGauge. The beam comes out and through the cavity. What you see when you're looking at the waveform is the peak here is the first interior peak of the wet cell, and then you have this big air gap, which is actually about 5,026 microns. I'm going to jot that down because we might use that number later. And then you see the back peak of the cuvette, interior interface of the cuvette. And what we'll do, and what I'm displaying in the upper right hand corner at the lower right portion of the upper right image is the optical thickness in microns. And we're going to monitor that as we make changes to this wet cell. First thing we're going to do is add some solution. In this case, water. Just getting a pipette. Okay, I'm back. Got the pipette. We'll drop some water in there and we'll see how that optical thickness changes. Anybody have a guess as to how that might change? Well, we'll see in a second. Okay, I've put in enough water that we have changed the reading of the optical thickness, and as you can see it got longer, so we have more optical thickness. And the reason that is because optical thickness is physical thickness times the index of refraction for the media that the beam is going through. In this case it's water, and water is about 1.34 refractive index for a 1310 nanometer group. Refractive index for water is a reasonable guess, and that equates to about 6,752 microns. I wrote that number down as well because we might use that one again too. And again, beam, to block the beam, you'll see the beam in front and you'll see both of the peaks disappear. Oh, here's the other thing that's going on. See these peaks? They're much lower. Why are they lower? Well, that's because the difference between the index of refraction of air and glass is much higher than the difference of the index of refraction for water and glass, and you get less back reflection in that case. Sometimes that's known as index matching. This is a very dramatic case of that, but we should probably raise the intensity of our signal, and I did that by raising the LED intensity in the OptiGauge, and you can see the peaks go up. So now we can, with confidence, measure a thickness as we make changes. So why are we measuring solution? So let's say you're making a saline for ophthalmic purposes or for irrigation purposes in surgery. You're basically adding a salt to water to make that saline. And I have salt in this container and water in here. And what we're going to do is we're going to add this and see how that optical thickness changes as we add salt to it. So here we go. I'm going to try to pour a little salt in. And of course it's difficult to do this slowly. So let's see, is that enough? Okay, so I threw in a little bit of salt. And now I'm going to start with my pointer here and see if we can't get it to dissolve a little bit. And what you'll see is as it's dissolving, let's see if we can see the beam passing through. Let's see if I can get it to show up. Well, no, we'll say we can't see that. If I put a lot in and made it murky, you could see the scattering, the salt crystals would scatter the beam and it would look like a little red beam going through the solution. Oh, and just a side note, the red beam doesn't do the measurement. That's just a pointing aid so that you can see where the actual 1310 nanometer sled beam is going, and they're absolutely coaxial. So what you see here is where that 1310 millimeter points, but the red is not really what's doing the measurement. And that's why I said a 1310 group refractive index. As I was talking about that, you can see that the optical thickness has started to settle in as the salt dissolves. I'm going to agitate it again and see if we can dissolve some more. And there we go. We're causing some more to dissolve, and look what's happening to the optical thickness. We started at 6,752, and now we're at 6,803. And it seems to be stabilizing a little bit around there. So by adding a certain amount of salt, which I didn't measure it, I just added some, I got a change in optical thickness. And the way it would work is if you were monitoring the process, you could take the time to pre-measure both your water and your saline and get a concentration level either by mass per mass, volume by volume, however you wanted to make the measurements, and know what optical thickness you would get for what level of ratio between the two masses of the liquid and the salt were. And that way you could build up a lookup table to tell you what optical thickness correlates and in fact calibrates to what concentration of salt you're adding to the system. And you can imagine that in a process you have a mixing chamber, and maybe there's a clear tube somewhere that allows you to pass the OptiGauge beam through. That ID of that tube should remain very consistent and be equivalent to this known precise cuvette separation. And then you can keep track of the optical thickness of the saline mix as the mixing progresses, and you could very accurately stop the process when you hit a specific optical thickness, and that would equate very, very accurately to a concentration level. So today in the lab we took a look at how you might be able to monitor a mixing process for saline simply by using the OptiGauge. Bye for now.